Rates of change in multivariable systems. Hello everyone. Let's begin our lesson on rates of change in multivariable systems. To start, let's look back at what we have already covered. In our previous sections, we focused on basic rates of change, where we analyzed how one single variable changes with respect to another. However, as we move into more complex applications, you will find that many real-world scenarios are not that simple. Often, a single quantity, such as the area of a shape or the volume of a container, depends on two or more different variables simultaneously. The crucial point to understand here is that all of these variables are changing at the same time with respect to time, which we represent as t. So, how do we find the rate of change for such a dependent quantity? First, we must differentiate the governing formula, the equation that relates the variables, with respect to time. In doing this, we must carefully apply the standard rules of differentiation. Specifically, we will be utilizing the sum rule and the product rule for each variable involved, both of which we will examine in detail in the following slides. Understanding the process. Now that we have established the concept of multivariable systems, let's walk through the actual process of solving these problems. First, it is crucial to understand that when multiple dimensions are changing simultaneously, we must treat each dimension as a function of time. For instance, instead of viewing x or y as static values, think of them as x of t and y of t. To ensure accuracy, I recommend following these 4 general steps. Step 1 is to identify the formula. Before doing any calculus, you must write down the mathematical relationship between your variables. Depending on the scenario, this might be the formula for area, volume, or perimeter. Step 2 is to differentiate with respect to time. You will apply the derivative operator, d over dt, to both sides of your equation. This allows us to see how the entire system evolves as time passes. Step 3 is to apply differentiation rules. This is the technical core of the process. You will use the chain rule for individual variables, and as we will explore in the next few slides, you must apply the product rule if your variables are multiplied together. Finally, step 4 is to substitute values. Once the differentiation is complete, you can plug in the instantaneous values of the dimensions and their specific rates of change to find your final numerical result. Case 1. Linear combinations, the sum rule. Now that we have established the general process for solving these problems, let's move on to our first scenario, linear combinations, where we utilize the sum rule. When the mathematical relationship between your variables is additive, meaning the variables are added together, you can simply differentiate each term individually. To illustrate this, let's look at the example of the perimeter of a rectangle. Imagine a rectangle where both the length, represented by x, and the width, represented by y, are increasing over time. The formula for the perimeter, p, is given as p equals 2 times the quantity x plus y. To find the rate at which the perimeter is changing with respect to time t, we follow a 3-step differentiation process. First, we differentiate both sides of the equation. This gives us the derivative of p with respect to t equals the derivative with respect to t of 2 times the quantity x plus y. Second, we apply the constant multiple rule. Since 2 is a constant, we can move it outside of the derivative operator. This simplifies our equation to the derivative of p with respect to t equals 2 times the derivative with respect to t of the quantity x plus y. Third, we apply the sum rule to the variables inside the parentheses. This results in the derivative of p with respect to t equals 2 times the sum of the derivative of x with respect to t and the derivative of y with respect to t. In this final expression, the derivative of x with respect to t represents the rate of change of the length, and the derivative of y with respect to t represents the rate of change of the width. This concludes how we handle additive relationships. However, in many real-world cases, variables are multiplied rather than added, which brings us to the product rule in the next slide. Case 2, Product Relationships, the Product Rule. Now that we have covered linear combinations and the sum rule, let's move on to Case 2, which deals with product relationships. When you encounter a scenario where two or more variables are multiplied together, you cannot simply differentiate them individually. Instead, you must apply the product rule. To state the rule formally, for any two functions, u and v, the derivative of the product uv with respect to time is equal to u times the derivative of v with respect to time, plus v times the derivative of u with respect to time. Let's illustrate this with a practical example. The area of a rectangle. We know that the area, A, is the product of its length, x, and its width, y. Therefore, our governing formula is A equals x times y. To find the rate at which the area is changing with respect to time, we begin by differentiating both sides of the equation. This gives us the derivative of A with respect to time equals the derivative of the product of x and y with respect to time. By applying the product rule we just discussed, the expression becomes the derivative of A with respect to time equals x times the derivative of y with respect to time, plus y times the derivative of x with respect to time. This resulting formula is very important because it reveals that the total change in area is not solely dependent on how fast the dimensions are changing, which are the derivatives of x and y with respect to time, but it is also influenced by the current size of the length and width at that specific moment. Now that we understand the theory behind the product rule, let's move to the next slide to see how this is applied in a real-world physics scenario. Real-world application example. Now that we have covered the theoretical framework of the product rule, let us apply these concepts to a practical, real-world scenario to see how they function in practice. Consider a rectangular metal plate that is being heated. Due to the process of thermal expansion, the plate is expanding in both dimensions. Specifically, its length, L, is increasing at a rate of 0.1 centimeters per second, and its width, W, is increasing at a rate of 0.05 centimeters per second. Our objective is to determine the rate at which the total area of the plate is increasing at the precise moment when the length is 10 centimeters, and the width is 6 centimeters. Let us walk through the solution step by step. In step 1, we begin by listing all the given information to ensure we have a clear starting point. We have the current length, L, which is 10 centimeters, and the current width, W, which is 6 centimeters. We also have the rates of change. The rate of change of length with respect to time is 0.1 centimeters per second, and the rate of change of width with respect to time is 0.05 centimeters per second. In step 2, we establish the mathematical relationship between our variables. Since we are dealing with a rectangle, the formula for area, A, is simply length, L, multiplied by width, W. Moving to step 3, we must find the rate of change of the area. As we discussed in the previous slide, because the length and width are multiplied together, we cannot simply multiply their rates. Instead, we must differentiate the formula with respect to time using the product rule. This gives us the following expression. The rate of change of area with respect to time equals the length times the rate of change of width, plus the width times the rate of change of length. In step 4, we substitute our known instantaneous values into this derivative. We plug in 10 for the length, 0.05 for the rate of change of width, 6 for the width, and 0.1 for the rate of change of length. Finally, in step 5, we perform the calculations. 10 multiplied by 0.05 equals 0.5, and 6 multiplied by 0.1 equals 0.6. Adding these two values together, we arrive at a final result of 1.1 square centimeters per second. In conclusion, the area of the metal plate is increasing at a rate of 1.1 square centimeters per second. Please take note of how we carefully distinguished between the static dimensions and their rates of change. This distinction is critical, and we will discuss some common pitfalls regarding this in the next slide. Common mistakes to avoid. Now that we have walked through a practical example with the metal plate, it is crucial to discuss some common pitfalls. Let's look at the common mistakes to avoid so you can ensure your calculations are accurate. First, let's talk about ignoring the product rule. A very frequent error students make is assuming that the derivative of x times y with respect to t is simply the derivative of x with respect to t multiplied by the derivative of y with respect to t. I want to be very clear. This is incorrect. As we saw in our previous example, you must always use the formal product rule, which is x times the derivative of y with respect to t, plus y times the derivative of x with respect to t. Secondly, be careful not to confuse static values with rates of change. In these problems, you are dealing with two different types of information. You have the dimension, for example, x equals 10, which is a snapshot of the size at a specific moment. Then, you have the rate of change of that dimension, which is the derivative of x with respect to t equals 2. If you accidentally substitute a rate where a dimension is required, or vice versa, your final answer will be incorrect. Always double-check whether the value you are plugging in is a measurement or a speed of change. Finally, keep a close eye on your sign errors. In the example we just solved, the metal plate was expanding, so our rates were positive. However, if a dimension is shrinking or decreasing over time, the rate of change must be expressed as a negative value. For instance, if the length is decreasing, you would write the derivative of x with respect to t equals negative 2 centimeters per second. Forgetting that negative sign will completely change the direction of your result. Keep these 3 points in mind as we move toward our final summary of the topic. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of these concepts. First, remember that in any multivariable system, the fundamental step is to differentiate your governing relationship formula with respect to time, t. As we saw in our discussion on the perimeter of a rectangle, when you encounter additive relationships, you should apply the sum rule. In mathematical terms, this means the derivative of x plus y with respect to t is equal to the derivative of x with respect to t plus the derivative of y with respect to t. Conversely, for multiplicative relationships, such as the area or volume examples we explored, you must use the product rule. To be clear, the derivative of x times y with respect to t is calculated as x times the derivative of y with respect to t, plus y times the derivative of x with respect to t. Finally, always keep in mind that the total rate of change of a combined quantity is not determined by a single factor. Instead, it depends on both the current instantaneous values of the variables and their individual rates of change. As we noted in the previous slide, distinguishing between these two is the key to avoiding common calculation errors. If you keep these rules in mind, you will be well equipped to handle more complex related rates problems.